series. And without further ado, let's start, and I look forward to the talk. Thank you, Elizabeth.
Thanks. Okay, let's have attempt two at this. Yeah, so I'm going to talk about counterexample guided inductive synthesis modulo theories. And the idea behind this algorithm is that it uses a theory solver to verify generalized candidate solutions and to return more general counterexamples. And by doing this, it's able to synthesize programs containing arbitrary constants that elude other solvers. So this is the outline of what I plan to talk about. So I'm going to give a bit of a sort of motivation, not too much of an overview of CGIS, because we've probably had most of that by this point. Then I'll dive into the algorithm in detail and the evaluation. I'll talk about, so as Andy mentioned, there's an implementation of this in CBC4, so I'll talk briefly about that. And then I want to quickly cover some ongoing work where we go beyond these arbitrary constants. So if you recall, CGIS is solving this problem of does there exist a program P for all inputs X such that this specification is satisfied, and the spec here I've used sigma to denote this. But this pattern of alternating between a learner and a verifier is very common in automated reasoning. And if we quickly step through how CGIS does this alternation, in a standard CGIS loop, your synthesizer will be looking for a program that works, that satisfies the spec for all Xi, where Xi is a subset of the possible inputs. And that subset is the counterexamples it's obtained so far. If it can't find one, then it'll say there's no program in your grammar. Not very many synthesizers will actually do that. If it can find a candidate, it'll then pass that candidate to the verifier, and the verifier then looks for a counterexample. Is there an X such that sigma isn't satisfied? And if no counterexample exists, then we have a solution. If one does exist, then we pass back this single value for X, the counterexample, to the synthesis phase, and then the loop repeats. This counterexample is appended to the Xi's. Now, I'm going to use an analogy to highlight one of the limitations of this counterexample guided alternating loop. So there's a guessing game that you might have played as a child, and the idea is it's a two-player game. Player one thinks of an object. I like to name my stick figures Alessandro and Daniel after my co-authors. So Alessandro thinks of an object, and Daniel tries to find out what that object is by asking questions that Alessandro can answer with a yes or a no. And this is a little bit like CGIS. So you can think of Daniel as being a bit like the synthesizer in CGIS. He's searching for a solution, and Alessandro is a bit like the verifier. He's checking Daniel's solution, and he's giving yes or no answers, whether it's right or wrong. And it's not quite like CGIS, because Alessandro is only giving single bit answers. He's only giving yes or no. He's not giving, whereas in CGIS you get a number, you get a literal counterexample rather than just a yes no. But let's ignore that for now. I want to focus on the main reason this is different to CGIS, which is that Daniel is asking questions about the solution, whereas in CGIS, the synthesizer doesn't ask questions about the candidate. It guesses complete candidates, and it just says, is this one right? Is this one right? Is this one right? And that would be a bit like playing the game like this. And clearly, this is quite silly. It's going to take Daniel a long time to get the right solution. In the worst case scenario, he has to enumerate through all of the possible objects in the universe. But CGIS doesn't do that, right? Does it? Does it? Well, actually, I'm going to tell you that sometimes it does. And so I'm gonna give you an example. This example is an invariant. So if we recall the invariants we had in the first talk, this is a safety invariant for a loop in some code. And we want to find an invariant such that it holds in the initial state and it holds after every iteration of the loop. And then...
Sorry to interrupt, we're still on slide 16. I thought you might want to know.
Oh, I don't have a solution for this. I'm on slide 25.
All right. I can share. Let's see.
You'll need me to stop sharing first.
Yes, just a second. And
you've missed a whole series of very excellent drawings.
So let's go from 16 to 25. And,
okay, so
here is the enumeration.
Yeah. Okay, so we have we're trying to find a safety invariant such that these properties hold. So it holds before the loop, it holds at every iteration of the loop, and if it holds after the loop, then the assertion is true. And if we skip to the next slide, it will give you an example solution just to save you having to work it out in your head. And there are multiple different answers to this. But if we have a look at how CGIS might tackle this, so if we jump onto the next slide, we can look at a way, so this would have been animated, and we can look at how CGIS might have tackled this. We jump into the middle of it solving it. It was looking for, it's looking for this possible solution that bounds X with an upper and a lower bound. But suppose that it's found the candidate solution X less than 95, and it passes that to the verifier. And the verifier looks at that and it says, no, this doesn't work when X is equal to 95, and gives that counterexample to the synthesizer. And the next solution we get may be X less than 96. And then the verifier will then say, well, that doesn't work for X equal to 96, and pass that back to the synthesizer, and so on. And you can see how this loop repeats, and we end up enumerating through X less than this constant literal, through all of the constant literals until we get to 1003, before we discover that we actually need a lower bound as well. And so if Daniel reaches a solution quicker by asking more general questions, can we do that in CGIS? The question is, can we go from the first illustration we had next slide? Can we go from the first illustration we had, where we're enumerating through objects, to asking more general questions in CGIS? And the answer is yes, otherwise I wouldn't be giving this talk. But let's first consider another difference between the game and CGIS. So in CGIS, the synthesizer and the verifier are working together. So if Daniel can ask better questions, perhaps Alessandro could give more informative general answers. And perhaps the game could go something like this. You're going to have to flip through a lot of slides now. So as Daniel names objects, Alessandro can provide more informative reasons why the objects are incorrect. And this is the key. This is another key point of CGIS-T. What we want to know is if Alessandro can be more helpful, then perhaps the CGIS verifier can be more helpful too. And if we skip forward a couple of slides, this is what CGIS-T is. CGIS-T is asking more general questions and giving more general answers. In essence, it's broadening the communication between the synthesizer and the verifier. So if we jump into some of the detail now, Seeger's T is inspired by DPLLT. So if we look at the next slide, DPLLT combines a theory solver with a propositional SAT solver. And what it does is it constructs this Boolean formula that's effectively a generalization of the original formula. And it finds an assignment to that Boolean formula. And then it passes that Boolean formula to a theory solver. And that tries to work out whether the assignment is possible on the original formula. And if it's not, it passes back a clause that blocks that assignment. And the more general the clause, the faster the solver. And Seeger's T, on the next slide, takes standard Seeger's and it appends a theory solver to it. So it attaches a first order theory solver to it on the next slide. And so what happens is when the verifier block finds a candidate program that doesn't work, it will generalize it and pass that to a theory solver. And then the theory solver will work out if the general program is a solution. And if not, it will produce a clause that blocks that general program. So we can see that when we get to the verifier, there are, in the original Seeger's loop, we send a counterexample immediately back to the synthesizer. If we go on to the next slide, what happens in Seeger's T is we take this candidate program P star and we generalize this program in a generalization phase. And I'm going to talk about one specific instance of generalization, which is based around constant literals. So what we do is we replace all of the constant literals in this candidate program by a vector of symbolic values, which gives us P star V. And other methods of generalization might be possible, but I'm going to focus on this specific instance. And then on the next slide, we can see that P star V is then passed to the deduction step. And the deduction step's job is to figure out if the generalized program could be a solution, and if not, to block the generalized program. So effectively, what it's doing is it's asking, does there exist a valuation for V that makes X less than V a valid invariant? And if there is, so it wants to say, can I find a V such that P star V is a solution? And if there is, it can then return that concrete solution. And if there isn't, it wants to block P star V with a clause. A key thing to notice here is that this is a first order formula because the quantifiers are over the variables. So that's Seeger's T, but the question is, what kind of theory solver do we need for this? And in the paper at CAV, we looked at two theory solvers. We looked at a standalone implementation of Fourier-Motzkin, and we looked at an SMT solver, so we used Z3. But essentially the requirements are, it must be able to solve first order formula with arbitrary propositional structure and with a single quantifier alternation. So if we skip to the next slide, we can look at how we do this in the implementation we have. So this formula potentially could take a while to solve, especially if it's SAT. So what we do is we'll split it into multiple parallel formula. And this could be done by a first order solver. And we simply did it because the solvers we had were overwhelmed with the formula we were giving them. And so what we've done is we've split it by adding constraints on the symbolic variables that we introduced. So bounding them with some constant C. And we've pulled this constant C out of the candidate program, but this is just a heuristic. You could bound it anywhere you like. You could bound it, like you could pick this constant however you like. We've got a heuristic that happens to work. So we can see on the example invariant we had a candidate that was X less than 95, and we've generalized that to get X less than V. And then we want to swap these, we want to bound these V variables with some constant. And we can see on the next slide that that constant is, that we use is 95. So this is still, so we solve these formula in parallel. These are still fairly hard formulas. So there are 3 different outcomes for these subproblems. They can either be sat, unsat, or they can time out. And what we do depends on the results. So on the next slide, we can see that if both are unsat, then we block the whole of P star. If one of them is unsat and the other one doesn't finish, then we return a constraint on V. So that constraint will say, if your candidate program is the same general structure as P star, then make sure the constants are within these bounds. And then obviously, if one of the formula is sat, then we've got a solution, and we can return a solution. And the final outcome is that neither finish within the timeout. And if they both time out, then we default to normal CGIS. So let's look at some results. We implemented our prototype over bit vector benchmarks without a syntactic template. And we compared to CVC4 because everybody compares to CVC4. So if we have a look at the graph a couple of slides ahead, in the original set of experimental results, we managed to solve more benchmarks than CVC4, although we were in general slower. It sort of keeps plodding on and eventually manages to solve them. And this is against CVC4 1.5. So on the next slide, I want to give CVC4 the credit it's due. We then compared to 1.7, and our comparison didn't go quite so well. But if we skip forward a bit, I can now talk about, there is now actually a CGIS-T implementation in CVC4. So the implementation is in CVC4 1.7 and onwards, and it uses itself as its own first order solver. And it supports CGIS-T with syntactic templates, which is nice. There are a couple of key differences. So when we implemented CGIS-T, we searched through concrete solutions, and CVC4 searches through templates in the synthesis phase, and then it passes those to the verifier. That's really the key difference. So it's searching through templates rather than needing to do the generalization phase. And on this set of results, I've given you the results for one specific use case where CGIS-T has turned out to be quite beneficial inside CVC4. And this is, so I think Andy briefly mentioned this. These are the invertibility conditions, which are used for, so I think they were used for floating point formula. And I think there was a CAV paper in 2019 on this. And we found that CGIS-T on these benchmarks, it solves, so we compared it against both the naive CGIS implementation inside CVC4, and there's an option in CVC4 where you simply add every constant that is in the specification onto the onto the grammar. We can stay on the results slide we're on, by the way. So we can see that we've managed to solve more benchmarks, and it's on average 20 seconds faster on the mutually solved benchmarks. So if you build this into a virtual best solver, you gain about 50 seconds. To conclude the CGIS-T section, we've solved program synthesis by can we skip to the next slide? So we've solved program synthesis via first order solvers that support quantifiers. And to do this, we've done this by verifying generalized candidate solutions and returning more general counterexamples. And the key thing to note is that this is broadening the communication channel between the synthesizer and the verifier. So if we flip forward a couple of slides, I want to talk about what I want to talk about briefly is how we can go beyond constants for this. So can we flip forward? Yeah, thank you. Yeah, so I talked about one specific type of generalization, which only works for constants. But one of the things that we're working on now is a framework that will allow us to expand this communication channel using Oracle guided synthesis. So the theoretical framework has been set out in the paper, A Theory of Formal Synthesis via Inductive Learning by Sushmit Jha and Sanjit Sesha. And the basic idea is that you have a synthesis phase or a learner and an oracle, and the communication between them is through a pattern of queries and responses. And so the queries are defined to be in some set of queries, and the responses are defined to be in some set of responses. So if we look at the illustration on the next slide, in the case of CGIS-T, the query is my program correct? And the response, there's a number of responses. So if we look at the next slide, the response can be either, yes, your program is correct, or it can be no, and all of the programs of this sort of structure are wrong, or no, but if I replace the constants in your program, then it is correct, or no, and if you're going to use a program that looks like this, that has this program structure, make sure the constants are in these ranges. And so what we want to do is we want to allow, so a future direction for CIGUS is that we want to, can we go on to the next slide? Is that we want to allow more like the user to specify the queries and the responses between the synthesizer and the oracle. And so we've introduced a syntactic extension into CIGUS if for this. And this would allow the user to specify how broad the query and response paths could be. And the question of what type of queries and responses could you have? Well, you could have any, provided that it can return some kind of logical constraint, provided the response can be some kind of logical constraint. So to conclude, I've talked about CGIS-T. The main point of CGIS-T is that broader communication between the verifier and the synthesizer is good. Broadening this communication allows you to reduce the search space faster. And I would argue that the main insight here is that the oracle should provide all of the information it has available if it would be useful to the synthesizer. But this, can we have the next slide? This does make the game quite short if you provide all the information you have. Are there any questions? And thank you for the fantastic slide changing.
Questions? Other questions from people? We do have 2 minutes to the official end. Okay, I'll start with the question. So is it correct to say that the current work, not the proposed future work, is related to inequalities where values come from numeric intervals, or is it currently more general than that already?
Do you mean the specific? So the current work basically will look for constant literals in your solution. So it will only work for problems where you need constant literals in the solution. There's no specific constraint over the type of specification you can have, though.
But I assume that the benefits usually occur when you have inequalities, right? And the counterexample is not specific enough because it is a loose bound on those intervals, or other cases where.
So it is true that's a case where you do benefit from it. I think that's not necessarily the cases where you find, so the cases where you benefit are typically the cases where you'll find that people, when they've written syntactic templates, have had to provide a constant literal in the syntactic template, or very specific constant literals. So examples of that might be, so things that involve bit vector manipulation, if you need to shift by some very specific number. like anything where your solution involves some kind of specific value that you might not have in the spec.
So I understand that, but I was curious whether in those cases where there are no inequalities, there are actually benefits from having the more general counterexamples. I guess the question becomes, would the more general counterexample block more solutions than a concrete one, right?
I think the real payoff comes. So the real payoff from CGST is that you manage to search for these search for the solution, the concrete solution within the general template. Like that's where you get the biggest gains rather than returning the counterexample. So CVC4 doesn't return the generalized counterexamples. It's only our prototype that returns the generalized counterexamples. So the payoff in the CVC4 implementation is that you're passing general solutions to the verifier, and then the verifier is trying to complete them.
Thank you. Do we have any additional questions? In that case, I want to thank Elizabeth and all the speakers here for fantastic presentations. Ružica, I assume we would love to collect the slides and post those in addition to the recorded talks, right?
In that case, we need to contact Ashley. So I will just ask all the speakers, and I will ask Ashley if she could. Ashley, if you're there, could we put slides online? Ashley's not there yet. Anyway, speakers for now, yes, just send your slides, please, to Ashley, and we will ask her if she could put them online because she's in the charge of maintaining the website. And also she was the one who contacted you for titles and abstracts and everything. She put everything online. So just for now, send slides to Ashley, and we will ask her if she could put them slides online. Thank you.
Thank you, and see you all next week. Bye-bye.